Welcome to Higher Structure Seminar Series of Feza Gürsey Center for Physics and Mathematics. Today our speaker is Emanuele Pavia from Luxembourg, and he will tell us about categorification of Koszul duality in algebraic topology. And we are very pleased to have Emanuele as one of our speakers. So please, Emanuele. Yeah.
Thanks for the invitation. It's a pleasure to give a talk for your higher structure seminar. So today I will tell you something about a work that is hopefully not more work in progress with Nicola Sibylle and James Pascalev about categorification of Koszul duality in algebraic topology. And my seminar will do something like this. We will start reviewing a bit of classical Koszul duality for operands, like the most general statement concerning the Koszul duality. And I'll review a bit of Koszul duality between modules over Koszul dual algebras due to Beilinson, Ginzburg, and Sergel. And then I will try to explain how this Koszul duality between modules actually in the topological setting can be realized from an algebraic geometric perspective. And for this, I will review a bit of the theory of derived stacks and some stacks associated to topological spaces. And finally, using this new perspective, I will generalize the setting for to the categorified setting, and namely to the categorified modules over EN Koszul dual algebras. And I will finally present the main result and a sketch of the proof with some consequences. So feel free to stop me anytime if you have questions. So for once, I will start by saying that in this talk, everything is implicitly derived. So I will say category and then category instead of infinity category or infinity and category. And limits, colimits, tensor products, mapping spaces, or spectra, etc. Everything is understood to be derived or homotopical. And also the notations like for the modules actually means the derived stable or differentially graded k-linear derived category of k-modules. And I use homological indexing conventions. So what is classical Koszul duality? There have been many formulations during the years concerning Koszul duality between algebras, coalgebras, etc. But the most general formulation essentially is a correspondence between operads and cooperads, between certain classes of operads and cooperads. So if you have an operad that is quadratic and Koszul, then by considering a bar and cobar construction, you can get like a correspondence. Okay, I cannot write. Okay, sorry. And so you can get a correspondence between the operads and the cooperads that relates the algebras and the coalgebras over them. So in particular, what you get is that usually if your operad is dualizable enough in the sense that the piecewise objects of the n-array operations are dualizable, and in some sense, in some stable or k-linear sense, then you can actually take a dual of the cooperad of the coalgebra that you get from the operatic bar-cobar construction and translate this correspondence into a correspondence between algebras of Koszul dual operads. So some classical example of Koszul dual operads are the augmented associative operad, which governs the augmented or non-unital associative algebras, which is Koszul dual to itself and up to operatic shift. And this usually is said that if you have an algebra, which is associative, and then what you get is that the A Koszul dual is the linear dual of an operatic bar construction. So you get these. and then you take, this is naturally a coalgebra, and then you take the dual. And okay, so for any integer n, in general, you have a little n-disk operand of better non-unital little n-disk operand, which governs non-unital En algebras. Again, this is a self-dual up to n-fold operatic shift. And for n equal 1, this is actually the same Koszul duality, the same self-Koszul duality from the associative augmented operand to itself. And if you get this to infinity, you get that the Koszul dual of the operand of the Lie algebras, or of the operand governing Lie algebras, is the operand of augmented commutative algebras, which is equivalently the non-unital infinity operand. And this, for example, was already observed by Quillen in the classical rational homotopy theory papers. And this is a core ingredient for many formulations of derived deformation theory. Okay, so let's suppose you have an operand O which admits a Koszul dual O-shriek, and suppose that the Koszul dual is involutive. It is not always the case. You need some smallness, finitely generation assumptions, but for all the examples that I provided before, this is true. So you have this bar-cobar type adjunction at the level of categories of algebras and O-shriek algebras. And so suppose now that C is the derived category of K modules over a commutative ring spectrum K, and take O to be the non-unital associative operand. As I was saying, what you get is this the Koszul dual algebra of an augmented associative algebra is just the self-exed algebra of the augmentation module. And for n greater or equal than 2, these the Dan additivity, which tells I recall that Dan additivity simply tells that EK algebras inside EK prime algebras are the same as EK plus K prime algebras. Then you can just iterate this bar construction. So you just take you take A, you take the Koszul dual, but now this is a EK minus 1 algebra, so you can keep going with the bar construction until you essentially are left without algebra structure, and so you get a En coalgebra. Take the dual and you get again En algebra. So, okay. So this is one classical example, actually the main example of this talk. So suppose you have a point CW complex, and so if you take the base loop space at the chosen base point, this is a group like E1 monoid. In a more classical setting, we can say that this is an H group. And so if you take any commutative ring spectrum, and you take the Pontryagin product induced by the H group structure of the base loop space, you get that the K-linear chains on omega x, which is understood as the smash product of spectra. So you take the suspension spectrum of the base loop space, you add a base point, and take the smash product with the K. This is an algebra. And if K is a classical commutative ring, this is indeed the algebra of K-valued chains. And this is now a Ni1 K algebra. And it is augmented because, of course, every space has a natural map to the point. And so by taking chains, you get an augmentation. Now, a classical result by Rosenberg and Sirrod yields an equivalence of commutative algebras. That is an equivalence between the Koszul dual of this chain. Here it should be here. Sorry, between the Koszul dual of the chain on the base of space and the cochains on X. And if, moreover, the space is of finite type, so you have only finitely many cells in each degree, and it is simply connected over a field, then this Koszul duality is actually involutive. So you can come back and get again the chain on the base of space by taking the Koszul dual of the cochain algebra. You can iterate for space which is now not simply connected but n-connected and of finite type over a field K, and you get an En Koszul duality of En algebras between these, because of course this is a each n H group. And so by taking chase, this is a En algebra. And so by taking the En Koszul dual, you still get the cochain algebra on X. So the cochain algebra is always commutative, so you can forget the commutative structure to any En algebra structure, and this is always the En Koszul dual of the iterated of the chains of the iterated loop space. Okay. And now let's recall this other construction by Beilinson, Ginsburg, and Circle. So take an augmented associative E1 algebra over a field K. Suppose that it is connected, so the pi 0 is K, and suppose that it is connective, so its underlying module is connective in the sense of classical homological algebra, and it is of finite type. Each homology group is, each homology K-vector space is finitely generated. Then the Koszul duality is involutive, and Beilinson, Ginsburg, and Sergel proved in their paper Koszul duality patterns in representation theory that there is an adjunction of where here we have the modules, the right modules on the Koszul dual, and the left modules on the first algebra. And this adjunction is of a tensor Ohm type. And the fact is that this adjunction is almost never an equivalence. It's very close to being one, but it's almost never one. Because here, if this was an equivalence, then in particular K should, the right adjoint should preserve all colimits, in particular filter colimits, and so K has to be a compact object. And in particular, it must not annihilate any non-zero module. So it must be a generator. And in practice, K may fail to be both of them. So let's see some examples from algebraic topology. So now let's assume that K is a field of characteristics 0, and let's study the adjunction for some Koszul dual associative algebras from that are chains or cochains algebras coming from certain topological spaces. The first example is CP infinity, the infinite dimensional projective space. So pick a base point, and you take the base loop space at this point, which is homotopy equivalent to the circle. So here now you have that the chain on S1 is just the symmetric algebra on K in degree 1. This is actually a complicated way to say that it is a square zero extension of K by K shifted in homological degree 1. While the Koszul dual, which is the cochain algebra on CP infinity, this is just a polynomial algebra with a generator beta in degree -2. And of course, K is not compact as a module, because of course K should be something like K plus K1, then you shift by 2 the algebra and you multiply by epsilon, and then you have to kill this copy of K, so you add another copy of the algebra and you go to infinity. So in particular, you have that it does not have a finite resolution, so it is not compact. And now take X to be the sphere, the topological two sphere, and again pick a point in X, and via the set spectral sequence, you can compute the homology of the base loop space, which is a polynomial algebra. Now it is not more graded commutative, it's only graded associative. It is a polynomial algebra with a generator U in degree, homological degree 1. The Koszul dual is just the cohomology of the sphere, which is just the quotient k beta mod beta square, with beta now in homological degree minus 2. In homological degree minus 2. Now what happens? It happens that k is U torsion here, because of course the augmentation is given by sending U to 0. So, but U is not torsion in KU. So you can consider the module obtained by inverting U. It is the localization essentially in the homological setting. And this module that you get in this way is now right orthogonal to K. So in particular, if you plug it here, this goes to 0. So you can see that K may fail to be both of them. It's not always a compact object or a generator. It may fail to be both of them. But the fact is that in order to make that adjunction and equivalence, we can just slightly modify the notion of modules on one side. And so let's introduce this piece of terminology. Take your augmented connective associative K algebra, just like the one that we have considered before. And we say that a left A module is null if its homology is totally finitely generated as a K vector space. So you take the homology, you forget that it was an A module, and you just look at it as a graded K vector space, and you ask it to be finitely generated. If you have that the zero homology of A up to nilpotence is K itself, then this category is just the smallest stable subcategory generated by extensions and finite colimits by K itself. And now, Bailinson, Ginsburg, and Sergel, the result can be formulated in more modern terms in this way. When A is connected and of finite type, so recall this means that pi 0 of A is K, and finite type, it means that it is finitely generated degree-wise, then the Koszul duality adjunction restricts to an equivalence between perfect modules on the Koszul dual and small modules on the algebra that you started with. So you take the incompletion on both sides, and here you get all right modules over the Koszul dual, and here you get the incompletion of small modules. This is called usually in the literature incoherent, but actually is different from usual incoherent in algebraic geometry. Indeed, notice that, for example, if you get an algebra, if A, for example, is K beta with beta in degree 2, then K A is not small, so it does not belong here, but still it is incoherent in the sense of algebraic geometry. So they are actually different. This is a clash of terminology, but it is quite standard. So the question is, of course, if we have seen that if you have E1 Koszul dual algebras, then you have this correspondence between their categories of modules. And is there a way to generalize this picture to the EN setting? So at least for EN algebras of the form base space, n-fold base space on X and cochains on X. And the fact that the difficulty lies in the fact that, of course, it cannot be an equivalence of modules, because if that was the case, then you would have that modules, right modules over these would be left modules, incoherent modules here would be equivalent to modules over the cochains, but these would be also inco over a iterated loop space when X is too connected, for example. And of course, this cannot happen because the categories of modules over iterated loop spaces are quite different in general. So we have to change the notion of modules that we are dealing with. In particular, we need to categorify them. And so this leads to the second question, because of course you have the categories of modules over a commutative algebra, which has some already some categorifications present in the literature, but on the other side we have incoherent modules over a non-commutative algebra. So what is the right categorified notion of module and incoherent module over IEN algebra? And this is where algebraic geometry enters the picture, because once we interpret these classical results by Bailyns and Gisberg and Circle with algebraic geometry, the right notion in order to categorify the statement are quite clear. So for the rest of this talk, I will use always a field of characteristics 0. Oops, sorry. And when I say a topological space, I will actually assume it to be both connected and pointed. If it is not simply connected, then I will assume that it is nilpotent, so that rational homotopy theory behaves well. And such that the rational homotopy groups, the k-rational homotopy groups, are finite in every degree. They are not bounded in general, but they are still finitely generated in every degree. And I will not make distinction between a topological space and its underlying fundamental infinity groupoid or homotopy type. So I will always denote X in both cases. Any questions so far? If not, I can continue. So let's review a bit the theory of derived stacks. So take the category of connective commutative K-algebras. So we are in characteristic 0, so you can imagine them to be commutative differential graded algebras, and put on them the derived algorithmic topology. A pre-stack is just a pre-sheaf with values in homotopy types, infinity groupoids or anima as you wish. And a stack is just a pre-stack satisfying descent for Étale topology. So it means that whenever you have a cover of an Étale cover of a scheme of an object, then if you take the check nerve, this is turned into it is turned into a limit diagram. And of course, if you have a connective commutative K-algebra, then it always co-represents an affine derived scheme that we denote as Pecard, just like in ordinary algebraic geometry. And we have this inclusion of categories. So we define the affine schemes as the opposite of the algebra of the category of commutative connective algebras. They sit inside stacks and they sit inside pre-stacks. And all these functors are fully faithful. So if in the derived setting, the derived category satisfies the descent for the Étale and actually for the flat topology. So for any stack X, we can define the category of quasi-coherent sheaves as a limit of categories in this way. And this category has good properties because it admits all limits and colimits. It is stable and k-linear. So if you see them as a differential graded category, it means that it is k-linear and pre-triangulated. And admits a symmetric monoidal structure given by the derived tensor product, which is compatible with colimits. And not always, but for many stacks of common practice, this is a presentable category in the sense that you have a small set of a small class of compact objects which generate everything else under colimits. And most importantly, the adjoint functor theorem holds. So a functor from QCOX to a presentable category is a left adjoint if and only if it preserves colimits. And given a topological space, you have two different stacks that you can associate to it. Because on one side, you have a very stupid idea. So you have X that associates a fundamental infinity groupoid in spaces. And so you can just take the constant stack that maps everything to spaces, and then just take the shiftification for the tal topology. And this stack is very linked to the theory of derived local systems on X, because it enjoys these properties. For once, the Betti stack is a up to size issue, is the left adjoint in a geometric morphism of infinite topoi, so it preserves all colimits. And so in particular, we have this, because any topological space in the homotopy category is a colimit of its contractible cells. And the base loop spaces are preserved. If you take the Betti stack of the base loop space, this is just taking the base loop stack of the Betti stack of X. So in particular, we can blur the distinction between these two. The category of quasi-Coherent sheaves is equivalent to the category of local systems, which is defined as a functor category. So here we are actually understanding X as a fundamental infinity groupoid, so it makes sense to consider the functors out of it into the category of K-modules. And the algebra of global sections is equivalent to the cochain K algebra of X. And this is just a straightforward computation. Everything actually follows from this small remark. And this is an important thing that is actually well known. In the classical setting, this is simply the fact that local systems are over connected spaces are equivalently representations of the fundamental group. And it comes in many flavors in the existing literature. But so suppose that you have the inclusion of the base pointer called eta, and then you can restrict a local system over X to along eta, and you get this. And the monodromy equivalence, as it's called, says the following. Whenever the target of the functor is co-complete, then this restriction induces an equivalence of symmetric monoidal categories as follows. So I need to write something here, because for once, this belongs to spaces, and the C is in general a category with all colimits. But the fact is that if C admits all colimits, then it admits an action of the category of spaces that is simply given by writing X as a colimit of shape X over its points. You take an object and you just send it to the colimit of shape X of the colimit of the constant diagram with value in C. So in particular, it makes sense to consider objects with an action of omega X. And not only that, but this is a symmetric monoidal equivalence. Why? Because, of course, actually, if C is symmetric monoidal, because here you have the pointwise tensor structure, while here you have the tensor product of representations. So it is the tensor product which makes the forgetful functor to C strongly monoidal. So in particular, if you take C to be mod K, this is just the underlying tensor product over K with the diagonal action of the base subspace. And not only that, but if C is symmetric monoidal, and so if C is symmetric monoidal with the unit pan C, then actually you can write the modules over omega x in C as modules over an algebra inside C, which is just the group algebra over omega x given by the diagram with constant value in the unit. For example, if C is mod K, this is just the homotopical version of the group ring of the omega x. And this will be important because this helps to relate the following result to the first main result with classical E1 Koszul duality. So let's go back to the overstack associated to a topological space, because of course you can take the cochain algebra on X, which is commutative now, and so even if it is not connective, it still defines a co-representable functor. You can just include every commutative algebra inside connective commutative algebra inside all commutative algebras and take the co-representable co-represented functor. And this is a coaffine stack as introduced by Toen and called coaffine by Lurie in its eighth paper in the series of derived algebraic geometry. And we denote this coaffine stack as a C-spec. I call them coaffine and C-spec in order to differentiate it between affine schemes and coaffine stacks. Because even if they share many properties with affine schemes, they're still a bit different in nature. Because it is still true that the global sections of C-spec is just the algebra you started with. It is still true that maps to a coaffine stack are the same as maps from the commutative algebra you started with to the global sections of the stack. But, for example, the natural functor from modules over C over the cochains to the quasi-coherent sheaves on the coaffine stack represented by the cochains is not an equivalence in general. And unless X is very, very simple, like a finite disjoint union of contractible components. In fact, we have the following result. So take a module over the cochain algebra of X and say that M is co-connective if it is just co-connective in the classical sense. But you say that it is connective if it is if this module is connective. So you first take the base change along the augmentation and then ask whether that is connective. Then take the quasi-coherent sheaves on C-spec and say that F is co-connective or connective if it is so when you restrict it to K modules along the augmentation, because of course you have C of X to K. This induces a map from spec K to C-spec of Cx, and so you can take the pullback along this map. You just ask that over here the pullback is connective or co-connective as a classical chain complex of K modules. And now these two rules define two right complete T structures on here and on here. But actually here it is also left complete, so it is both left and right complete. And the natural functor here is just a left completion of the left-hand side. This means that this is the universal category with a left complete T structure and a T-exact functor from mod over cochains. So in particular, this implies that this is an equivalence for any n. But for objects that are unbounded, it may fail, and actually it fails to be an equivalence most of the times. But this is a result that is very close in spirit to the Ginsburg-Sergel result. And in fact, we have the following. So since both X-Betty and the coaffine stack of the cochains have global sections equivalent to the cochains, you have that if you take the identity on the cochains, you get a map between these two stacks, which we call the affinization map. I say we call, but actually it's called like that in the literature, and it is not an invention of ours. And what we proved is that when X is simply connected, plus all the assumptions that I told you before, so it is of finite type, etc., then the affinization mapping uses a T-exact and co-limit preserving symmetric monoidal equivalence, like this. Of course, this is symmetric monoidal because it is a category of quasi-coherent sheaves. This is symmetric monoidal under the pointwise monoidal structure. And this composition, this is the monodromy equivalence. This is the inverse of the affinization map. And this is the natural functor, the right adjoint of the functor that goes in this direction. This is just the right adjoint in the Koszul duality adjunction of Beilinson, Ginsburg, and Sergel. And so in particular, this means that it is just R om over C omega x k. And how it is proved, this thing? Well, we adapt a result by Gaitsgory, which deals with ordinary incoherent sheaves in algebraic geometry. And we first put a natural T-structure here, essentially by restricting the T-structure of modules over omega x. And then we proved that when we incomplete this T-structure, then this is a left completion functor. So next, we proved that the Koszul duality equivalence of Ginsburg, Sergel, and Beilinson is T-exact. So it has to induce an equivalence between the left completions. So in particular, this implies that these two are equivalent. And next, we have to prove that the functor that realizes this equivalence is precisely the affinization map. And in order to do so, we study this functor. So a functor like this is always completely characterized by this composition. And the fact that this composition is very easy to understand, because when we forget the omega x structure and we get to mod k, this is precisely the tensor product over Cx with K. So this is the left adjoint in the Koszul duality. So this gives a glimpse of the fact that the Koszul duality of modules is actually a statement in algebraic geometry rather than a pure algebraic statement. And so the idea is that rather taking quasi-coherent sheaves here, we should categorify QCO on both sides, because indeed they are both quasi-coherent sheaves on derived stacks.
Can
And
I
you know,
ask a question?
yes,
A very naive question. The symmetric monoidal categories that you encounter, do they also have Tanakian structure? I mean,
uh,
Tanaka category, do you think?
indeed, this should be a Tanakian, because of course you have here, you have a fiber functor to mod
Okay.
K,
So
and
they have fiber functors. I
exactly,
see. Yeah.
exactly. In fact, this is the category of local systems.
Right.
This is the monodal under the stalkwise tensor product, and this is just the restriction to a fiber. So it is a symmetric monoidal. And this is the tensor product of representation. This is not the relative tensor product over the algebra, because of course the relative tensor product is in general only in one monoidal.
I see. So
While
so this is actually a representation category.
exactly. This in fact is a rep of omega x inside mod k.
Yeah,
Exactly.
yeah. Thank you. Yeah.
Okay, so the next step is then to translate quasi-coherent sheaves into something higher, like categorified quasi-coherent sheaves. And this is achieved using the formalism of presentable N categories developed by very recently by Stefanich and Kwaoki. So this is a very technical part, so I will try to be fast about that. So for any regular cardinal kappa, you just fix the size of the objects that compactly generate a category, and we call them we call the category of these categories the category of kappa compactly generated categories. And of course, we are admitting only functors that preserve colimits and kappa compact objects. So with this thing, this is kappa compactly generated itself. So we can take these, we can just fix for 1 to be itself, and for n, we take the modules over n minus 1. So for example, 2 PRL kappa will be mod over PRL kappa inside PRL kappa, etc., etc. And we define the n plus 1 category of presentable n categories in this way. We take this thing for any regular kappa that is admitted by the theory and take the union. And of course, we can take also k-linear coefficients over a commutative ring just by replacing here PRL kappa with mod k PRL kappa, and then just doing the same thing altogether. And these n categories share some similarities with presentable categories. Because, for example, for n equal 1, they are just the ordinary, this is just the ordinary 2 category of presentable categories and colimit preserving functors. And in general, for any n, the n category PRL n-1 is an object in PRL n. So in particular, this will be an object in PRL infinity 2, etc., etc. All these categories admit colimits, and a symmetric monoidal structure compatible with colimits for which the unit is precisely PRL n-1. And the category PRL infinity n admits also limits over left adjointable diagrams, in the sense that if you have a functor like this, and for any k and j, this admits a left adjoint, then you can just consider diagram of left adjoints and consider the colimit there. This is a standard computation with presentable categories and pre-triangulated differential graded categories. The fact is that for greater n, these in general do not admit all limits and do not admit all internal mapping objects. So it's still a bit trickier, like the adjoint functor theorem fails for presentable n categories. But still, the analogy is quite robust to do algebra with them. And so we can attack the problem of categorifying modules. So consider a EK K-algebra for a k greater or equal than 1. And we fix for n equals 0 the one category of left modules over R. For greater n's, but always lesser or equal than k, we consider these. Of course, we need to fix this bound because we use the monoidal structure on R. And after a while, after taking enough categories of modules, we finish the monoidal structures, so will not be an algebra anymore. Of course, if R is commutative, then we do not incur in this problem. And we call these categories the categories of n-fold left R modules. And for n greater or equal than 1, this is just another name for the n+1 category of R linear presentable n categories. They are really the same construction. And when you have a morphism of EK rings, you have an induced base change functor in this way. Because, of course, you have that this functor is symmetric monoidal by definition. And so it lifts to the categories of modules. And so you iterate this construction. And for n greater or equal than 2, there is a difference with ordinary theory because differently from, of course, if you have an algebra R, it is in general very difficult for it to be dualizable as a module. You need it to be, the underlying object has to be projective and finitely generated, bounded and finitely generated. But for n greater or equal than 2, this is always dualizable, and the dual is just the categories of R modules over the same algebra. So in particular, if R and S are both commutative, the base change functor is a part of an ambidextrous adjunction. This is just the tensor over L mod n-1 like this, and this is a forgetful. Of course, this will be the left adjoint by taking the ohm, but since this is self-dual, then taking the ohm is just like tensoring with the dual, which is itself. So this is why this is both a left and a right adjoint on both sides. And this is a trick that helps us to define a left-hand extension for any stack of these categories, because in general, of course, as we said, these may not exist. But since now every functor that we are considering is both a left and right adjoint, we can pass to the adjoint diagram and take the colimit. This exists. So this definition makes sense. And we call this the n+1 category of quasi-coherent sheaves of presentable n categories. Usually we will say just quasi-coherent sheaves of n categories. And this for n equal 1 was already defined by Gaisgori. And for n equals 0, this is just understood to be the ordinary category of quasi-coherent sheaves. And of course, this is always presentable, is always n+1 presentable. And is symmetric monoidal compatibly with colimits. And the fact that you have the ambidextrous adjunction at the level of categories of modules reflects on the fact that you have still an ambidextrous adjunction also when you consider morphisms of stats. And not only that, since everything is very rigid, because everything is both a limit but also a colimit and everything is almost dualizable, etc., the categorical Kunet formula holds without any assumption on x and y. You always can bring a product outside and consider a tensor product. So it is very easy in some way to manipulate these objects. And so we just look at what happens to the quasi-coherent sheaves over Betti stacks when you categorify. And essentially because both of these are limits with shape of x of these, you can see that these are just, shift cut and x Betti. you can see that the fact that they are related to, that quasi-coherent sheaves are related to local systems extends to the categorified setting. And so we call them just local systems of n categories. And not only that, the monodromy equivalence applies also in this setting because this is co-complete. So you get this. Again, this is the convolution product. And this means that, again, is a category of representations of omega x. So if you prefer, this is a representations. Okay. And when x is simply connected, then what happens is that this is again representations of the double loop space inside PRL infinity n minus 1. And so you can, if x is enough connected, you can iterate and you get this. So you already start seeing that we get the n-fold loop space coming, the categorified modules over the n-fold loop space in this picture. And so we get to the main theorem of our work. So fix n an integer greater or equal than 1. Suppose that x is unconnected plus those finite assumptions on these homotopy groups. Then the affinization map between these two stats induces an equivalence of n categories, which is this one. Okay? So in particular, by composing with the monodromy equivalence, you get that there is a correspondence between n minus 1 categorified sheaves of categories over the cospectrum of the cochains and n minus 1 categorified modules over the n-fold base loop space. So these were En Koszul duals, and this really unifies the picture of the Koszul duality between modules. So I also prepared some sketch, not so brief sketch of the proof of this. I will try to be as fast as possible. So for n equal 1, this is just the same thing that we did before. Really nothing new. For any n greater or equal than 2, we have this commutative diagram where this is always both monadic and comonadic, because under this equivalence, this is just a forgetful functor. And on the other side, this is conservative, and it is a left adjoint. The fact that it is conservative is because essentially any morphism to a connective target from Cx factors through the augmentation. So in particular, if something becomes an equivalence here, then it is an equivalence over any local sections, and so it is an equivalence. So in order to check that this is an equivalence by Barbeck-Lurie, is simply they need to be equivalent comonads. So you take the right adjoints and prove that this diagram still commutes. And the fact is that to make this diagram commute, we need to check that this is an equivalence for any C. And here is the trick part, because if n is greater or equal than 3, then this limit is also a co-limit, so we can bring it inside, turn it into a limit back again, and now by descent, this is just this. So for n greater or equal than 3, this rigidity of presentable n categories really makes it quite easy, because then by induction, you are just reduced to prove that these and these are equivalent, and then you are done. But the fact is that for n equal to, this thing is not obvious at all. Actually, it is true a posteriori, but you cannot bring the limit inside the tensor product with these. And so we actually need here some other workaround. For once, notice that if this was true, So if we can write shift cut over the cospectrum of Cx as this, here notice that is omega x, then by applying E1 Koszul duality, which we have already established, we can write these as local systems over omega x, and this by the monodromy equivalence, we know that it is local systems of categories over x. And here there is a result by Categorification that tells us that this is true. So this is true when this functor that is given by taking a category here, and on every local section, on every affine scheme over the cospectrum of omega x, we take this local section. We just take the base change. Okay? If this is fully faithful, then this is true. And here, surprisingly, enters the picture the rational homotopy theory, because in order to prove that that thing is fully faithful for omega x, we prove it in general for any H space Y, because in a rational homotopy theory, each H space, each rational H space factors as a product over its Eilenberg-MacLane spaces, and we can write it as a colimit. In general, it is only a limit, but since we have always sections, we can write a colimit as well. And so, essentially, since everything is well behaved under limits and tensor product and products, we are just reduced to prove this statement for this. And this is a straightforward computation using also results established by Categorification. So this ends the proof. And actually, it bears some consequences also for in algebraic geometry as well, because since we have this equivalence, we can use algebraic topology in order to study problems from algebraic geometry. For example, in his paper over one affineness, Categorification defined a stack to be one affine if the functor that I defined previously, this again takes C to C tensor Q co X over mod R for any affine scheme over X. If this is an equivalence, then we say that X is one affine. It's a categorification of the notion of being affine. And he proved that over a field of characteristic 0, the loopings of the additive group is affine until k equal 3, and it is not affine for k equal 4. Then his strategy stops because in some sense he used the results concerning the previous delooping in order to tackle the point, the further delooping. And the fact is that with algebraic topology, we do not incur this problem anymore. And so, for example, we prove that for any k greater or equal than 3, the odd deloopings of the additive group are one affine, and the even deloopings are not. So, in some sense, the twofold delooping of GA is one affine because it is not connected enough for Koszul duality for modules to hold. So this is a curious consequence of our work. And so I almost finished my time, so I finish with this question. This statement makes sense over any field, also over fields of characteristic P. And in fact, the proof for n equal 1 and n greater or equal than 3 does not really require the assumption on the field. Of course, you do not have to consider infinity rings, but you have to consider derived commutative rings, so simplicial and cosimplicial commutative rings, but everything works as well because it's very formal. Of course, we used the rational homotopy theory very, very crucially in the proof of the n equal 2 case. So the natural question is, can we find a workaround in order to avoid rational homotopy theory and generalize this result to to characteristic P fields? And this is something that I still do not know. So thanks for your attention. This is some literature.
Thank you very much, Emanuel. So, any questions or comments? So maybe I have a rather general question. The result of Gates-Gorey, is it used in his proof of geometric Lagrange?
I think that he uses this one,
Yeah.
usually uses with a group pre-stack anyway.
Uh-huh.
So and then he proves that if you replace these with BG, then this is true. And these are all results that he uses in order to prove that the RAM stack is one affine
I see.
for a sufficiently nice. I do not remember which group or. But anyway, he uses like one affineness was introduced to tackle geometric Lagrange.
In your work, you use Betty stack, right?
Yes.
Is there some comparison isomorphism kind of thing between these stacks?
Between the RAM and the Betty, you say?
Yes.
Actually, I think that in the algebraic setting, this is not true, but there is a different notion of analytic Betty stack due to Scholz, which the analytic Riemann-Hilbert correspondence provides an equivalence of analytic stacks between the analytic Betty and analytic de Rham. And in fact, there is another work, another paper of mine with another collaborator, Matteo Montagnani, in which we studied the problem of one affinities in the analytic setting. And we proved that for a sufficiently nice topological space, X, then the analytic Betty stack is one affine, and so also the analytic DRAM. And it is one affine in a way greater generality than the algebraic Betty stack. In fact, the algebraic Betty stack is often not one affine.
I see. Thank you. Any comments or questions? Okay, so let's thank Emmanuel once more. Uh, Very technical and let me say cutting edge theory. I mean, and we all wish success in your research.
Thanks.
And please follow our seminars and our YouTube channel also. So,
Yes.
uh, 2 weeks from now, Semih Özlem will talk on motives and machine learning, apparently. So we will see what it is. So now I'm closing the recording. Wait a second.
Okay.
I stopped recording, stop cloud recording.